Welcome. In this lecture, we're going to look at kernel-based support vector machines for performing classification. So our objective is, first of all, we're going to reformulate the linear max margin classifier in terms of its support vectors using the results we derived in the previous lecture on kernel regression. Then we'll derive a kernel version of Hinge loss with ridge regression, and that leads us to the support vector machine, which we will explore some of the features of in concluding. So recall that if we have a collection of data points and they're linearly separable, as I've illustrated in this diagram here, where the blue data points correspond to one particular category and the red data points correspond to the other category, we can decide to define a classifier that maximizes the margin. In other words, it splits the largest difference we can find between these sets of data points. The difference here, or the distance, is 2 over W tilde, where W tilde is the component of the classifier weights that is applied to the data, excluding the constant term that we add to get an offset. So we're going to represent that constant separately here in terms of B. Of course, if I define the feature vector x to include a constant term, then I write this as x transpose W, which is what we've been doing all along. So B is involved in the distance of the decision boundary in the solid green line here from the origin. Now the decision boundary only depends on, in this case, these 3 data points circled in orange, because these samples completely define the boundary for the max margin classifier. In other words, the boundary is not affected by these measurements that I'm circling up here in the upper left, or these red ones down here in the lower right. So the decision boundary depends only on these points, which we're calling support vectors. The other data points don't affect the decision boundary. Now recall what we did in kernel regression. We wrote a function d of x as phi transpose of x times w, where phi was a high-dimensional feature space derived from the measured data x. And we showed that we could write d of x as a weighted sum of kernels where we're evaluating the kernel at both x and the jth training sample xj. And then we found what these weights needed to be. Well, let's apply this kernel representation for regression in the case where we don't have a higher dimensional feature space. In other words, where we let phi of x be equal to x. In this case, the kernel is just the inner product between x and xj, and we see that d of x then becomes the sum from j equals 1 to n alpha j times the kernel, which is x transpose xj. X here does not depend on j, the index of summation, so I can pull that out and write d of x as x transpose times this sum of alpha j xj. Well, I can think of this sum then as the w that I'm applying in this particular case. So my w, my classifier weights, are going to be the sum from j equals 1 to n alpha j times x sup j, the jth training sample. So here, the advantage of writing it this way is we can see the explicit dependence of the weights on the training samples. And since we've already reasoned that most of these training samples don't affect the boundary at all, it's just these couple that are circled here, the alphas for those are going to be 0. Okay, so all the alpha j's except the ones corresponding to the support vectors are going to be 0. So this formulation of W expresses it in terms of a sparse solution. Recall that finding the max margin classifier involves solving an optimization problem. We don't have a closed form solution, so we've had to come to these conclusions here by reasoning simply that these training samples, which are far from the decision boundary, can't affect the performance, and therefore the alpha j's are 0. This turns out to be actually true when one solves the optimization problem as well. So suppose we do want to work in a high-dimensional feature space so we can implement nonlinear decision boundaries. Well, in that case, we're going to take x and replace it by phi of x. For example, we could take quadratic functions of all the elements of x, and things like x1 squared, x2 squared, or the cross products between xi and xj, and then the linear terms, just the individual x's, and maybe a constant term as well. Well, this will give us a nonlinear decision boundary. we can write our predicted class d hat of x as the sign of this inner product phi transpose of x times w. Now, when we look at solving for w, one of the ways we proposed to do that was to use hinge loss with ridge regression. So in that case, we're going to minimize over the sum of the training samples the 1 minus di phi transpose of xi times w, and we're taking the positive part of that quantity. Remember, this positive part symbol is if the argument in here is positive, we return that value. If the argument is negative, we return 0. And this is the hinge loss. So when di has the same sign as phi of xi transpose w, we have the potential of this quantity, 1 minus that, being negative. That will give us values over here which don't contribute any error because we're making the correct decision. di has the same sign as phi transpose of xi w. Now, if di and phi transpose of xi w have different signs, then we're going to be making this quantity larger than 1, and that's going to contribute to our loss function. And then we have our ridge regression, which is just lambda times the 2 norm squared of our weights w. Well, I'm going to make the claim that when we solve this problem, w has to be a linear function of the phi of xj. So we can write w as the sum from j equals 1 to n phi of xj times alpha j. And I've included a proof of that in the notes that accompany this lecture. So we're going to use this kernel trick, which as it's called, although it's not really a trick, it's just a substitution, to obtain our support vector machine. So recall, at the end of the last page, I asserted that I could write w, my classifier, as the sum from j equals 1 to n alpha j phi of xj. So we can rewrite our hinge loss with ridge regression by substituting for w. I've got 1 minus di phi transpose of xi, and then instead of w here, I'm going to write the sum from j equals 1 to n alpha j phi of xj, and that whole quantity, we're going to take the positive part again, since we're dealing with hinge loss. And then we'd have the ridge regression, which would be lambda times the 2 norm squared of w, which we'll write as lambda times w transpose w. And again, substituting for w with our expression that we've obtained. So we can do a little bit of algebra. I'm going to bring the phi transpose of xi inside the sum, and I'm going to combine the two sums on the right as we have down here. And again, so in both cases, I see there's a phi transpose xi phi of xj. Over here, I have phi transpose xi phi of xj. And when we did kernel regression, we had a similar inner product, and we said we were going to replace that with the kernel k. And this is the so-called kernel trick. So if we make this substitution, replace those inner products with k, the kernel, we obtain the specification for the support vector machine. That is, we're going to minimize over these unknown coefficients alpha j, this quantity. We've got 1 minus di times the sum from j equals 1 to n alpha j k of xi comma xj plus lambda times the sum I equals 1 to n, j equals 1 to n, alpha I, alpha j, k xi comma xj. Now, it turns out, as in the linear case, when we go into this higher dimensional feature space, we end up with a sparse solution for alpha once again. So in this case, our decision boundary can be written as d of x equals 0, because remember, we're making our decision based on the sign of phi transpose of x times w. And since phi transpose of x times w is just a sum from j equals 1 to n alpha j k, the kernel evaluated at x comma xj. And if I have some points here, you can see that maybe the correct decision boundary would bend around like this. Clearly, a linear decision boundary is not capable of separating these training samples. So let's suppose this green line is indeed the boundary. Well, again, since our hinge loss is not affected by these samples which are far away from the boundary, we can conclude that the alphas associated with those sample points, with those values of xj, have to be 0. And that this actual boundary only depends on these support vectors. So I've just picked a few to illustrate that perhaps it's this set of points, but it's these points in the neighborhood that are going to be able to define the boundary for us. Again, these faraway points can't contribute. So we're going to expect that our solution for alpha should be sparse. Now remember, the kernel measures the similarity or alignment of the two vectors. And we talked about kernels involving inner products of u and v, but the most commonly used one is the Gaussian kernel, and that one takes the 2 norm of the difference between u and v, and it puts that in an exponential normalized by 2 sigma squared. So this creates a bump. So if I have a point v here centered on that point, I have high values. If I go in directions u far away from v, the 2 norm squared increases, which makes this exponent argument more negative, and therefore the value gets smaller. So we can think of this as a bump or a raised surface that has circular contours and Gaussian cross sections. So in this case, it's telling us how close u and v are together. And you can imagine that if I place some of these Gaussian shaped bumps here and here and here and here and here and here, if I put Gaussian bumps on the boundaries, and maybe I have the alphas associated with the bumps that are in blue, I have those be negative, so those are downward or negative values, and I put positive values on the alphas associated with the bumps in red, then in the middle I'm going to go from negative to positive, which is where my decision boundary lies. So we don't need to put any kernels over here at data that's far from the boundary because, again, it's going to decay and it won't really help us shift the boundary very much. So those alphas are going to be 0. Now the support vector machine, where we're optimizing the hinge loss with this ridge regression penalty, it's not something that we can solve in closed form, but it can be easily solved using gradient descent. So that's what we'll do to find alpha. And we'd have to use a subgradient technique again because hinge loss is not differentiable. So these support vector machines are very powerful for classification and in many cases can achieve similar results to neural nets with implementing nonlinear decision boundaries.